Hello everyone, welcome to my class of statistics. I am King from the Public Health Department of Statistics. Last class, we have finished at the chapter 5, one sample statistical inference. And this class, we will finish the chapter 5. At first, let's review what we have learned last week. Last week, in chapter 5, we are talking about the method of one sample test for the mean of a normal distribution with known variance. And we also learned a method which is used for estimation the parameters of a population based on Z distribution. So the first method is used for hypothesis test. It's based on normal distribution, and most often we call a normal distribution as Z distribution. So we call it a method of Z-test. So Z-test is one of the hypothesis tests. It follows the same procedure with the other method of hypothesis test. And we have mentioned that in a hypothesis test, we have 3 steps. That is, step 1, to make 2 statements. The first one is H0. Actually, it is the null hypothesis. And the null hypothesis is what we want to know if it was true or not. We need to test the null hypothesis with the data of the sample. If the null hypothesis is rejected, that means the opposite situation should be true. So we need another hypothesis, another statement in step 1. That is HA, alternative hypothesis. And alternative hypothesis is in opposite against H0. In step 2, we need to calculate some special numbers. That special number is a kind of test statistic. We need to use the number of the test statistic to obtain its corresponding probability. So in this step, we need to do some calculation with the data of the sample, and we can get the test statistic based on some special formula. For example, in the test, we can use the formula of Z value to get the Z value. That is the test statistic. And the last step, that is step 3. In step 3, we need to compare the probability what we can get from the appendix tables with the standard value, that is alpha. And alpha is the significance level. Most often we use 0.05 as the number of alpha. So in step 3, we need to compare the probability with 0.05. We use the capital P to represent the probability. So if the P is bigger than alpha, that means it's bigger than 0.05, we cannot reject H0. But if P is less than alpha or P is equal to alpha, we need to reject H0. When we cannot reject H0, that means there are no difference between the two populations. But if we can reject H0, that means there must be significantly difference between the two populations. So that is what we have learned last class. And in last class, we have also learned method for estimation the parameter. That is confidence intervals based on Z distribution. We have explained how can we get the formula of the confidence interval. Most often, we use 1 minus alpha confidence interval to estimate the population parameter, for example, the population mean. And we have explained how can we get the formula. This formula is based on Z distribution. And we said that the confidence interval is normally used when an interval estimate of mu is desired, in which the probability of the interval actually covering mu is 1 minus alpha. So that means the confidence interval, which is bounded by two numbers. The first one is the lower bound, and the second one is the upper bound. So the confidence interval is the range between these two numbers. And we said that the range has a special probability to cover the population parameter, for example, population mean. And the probability should be 1 minus alpha. Most often, we use 0.05 as the number of alpha. So we usually get 95% confidence interval. So that means the range has the probability of 95% to contain the population mean. Okay, so that's what we have learned last class. This class, we will continue to finish the chapter 5. So, in today's class, we need to talk about another method used for one sample. We call it one sample t-test. So we can find that it's different from what we have learned last class. What we have learned last class is a method called z-test, one sample z-test. But this class we are talking about, it's still used for one sample, but not z-test, but t-test. So here we can find that this method is also used one sample. And I think we have learned what's the meaning of one sample last week. Let's review it. One sample. So how do you know whether is it a question of one sample? Yes, you need to find a special number, that is the sample size, the little n. Sample size denoted by the little n. So if you can find the single number of sample size in a question, that means it must be one sample. So here in this kind of question, we can find only one sample and a given population. So we need to use the given sample to infer the underlying population of the sample with the given population. So we need to compare if there is any difference between these two populations, but the underlying population is not given. So we need to use the data of the sample, which is randomly drawn from the ungiven population. So that is the meaning of one sample. So what's the meaning of t-test? What's the meaning of this little t? That is a special distribution, similar with the z distribution, but it's different with the z distribution. So I will explain what's the meaning of t distribution. But the first one you should know is the precondition for t-test. Let's think about what is the precondition for z-test. We have talked about that last week. Z-test is used only when sigma, that is the standard deviation, or sigma square, that is the variance. When sigma or sigma square is given, we can use z-test. And we said that x, the original data x, follows a normal distribution, follows a z distribution. So we use z-test. That is a method based on z distribution. But what can we do if sigma is not given? When sigma is unknown, we cannot use z-test because the original data doesn't follow a normal distribution. It follows another special distribution, that is t-distribution. Okay. So how can we get t-distribution? Let's think about it. This is the formula. This is the formula for z value. We have learned that last class. And this is mu, the population mean. This is the sigma, the standard deviation of the population. This is the sample mean x bar, and this is the z value. And we know that we can get the z value from the appendix table A1. From that table, if we know the probability, we can get its corresponding z value. And we said that the probability should be the significance level, or we can say that the probability is actually alpha. So when we set the number of 0.05 as alpha, that means we can get the z value from table A1. And mu is not given in the question, but in the hypothesis test, in the first step, we will make a statement. That is, mu is equal to the given mu. We use mu0 to represent as the given population mean. So H0 should be mu is equal to mu0. So this number is known actually, right? Because this mu equals to mu0. And how about this one? Sigma. When we are talking about the sigma, that is the standard deviation of original data x. But I think I have mentioned that before. The population parameter is usually not given. So sigma most often is unknown. So when sigma is unknown, how can we do that? We can use the point estimation. So that means we can use S to represent sigma. Because we think we use S to represent sigma. Because in the point estimation, we will think that S is equal to sigma. So we use S to represent sigma. So here, this number is not sigma anymore, it's S. We use S to replace its value of sigma. But actually, we know that S and sigma are they the same? Do you believe S is really equal to sigma? Do you think that? Alright, S is actually not exactly equal to sigma, because we have mentioned a very important definition in chapter 4, that is standard error, right? Standard error means the standard deviation of x bar. And we said that when we draw a small part, or to say when we draw a sample from the population, and we can figure out some sample statistics with the data of the sample, and we will find that the population parameter is not exactly equal to the sample statistics, because population is so big, but the sample is so small. So S is not exactly equal to sigma. But if we do know the number of sigma and we decide to use the number of S to replace sigma, we will find that this ratio will not exactly equal to Z value. So that means when we replace sigma with S, the test statistic, this is the test statistic, that is the ratio, I have mentioned that. The ratio will no longer follow the standard normal distribution. That means the test statistic no longer follows the Z distribution. So we cannot use the Z test. And we will find that the test statistic follows a new special distribution, and we call that special distribution as t-distribution. We use the little t to represent the new distribution. So, what is t-distribution? We all know that the z-distribution curve is symmetric about z equals to 0, right? And we have already known that the t-distribution and the formula for t-value is actually x bar minus mu over s over square root n, right? So here we will find that the t-distribution is similar with the z-distribution. So t-distribution curve is still symmetric. It's symmetric about 0, but that is t equals to 0, because the distribution is t-distribution, not z-distribution. So it should be t equals to 0. And we will find that this part. Let's compare the t-distribution with z-distribution. This is the formula for z value, and we said that if the original data is not x but x bar, the formula should be like this. It should be like this. And here we replace the sigma with the data of s, and we will find that the t-distribution will be influenced by the number of the little n, the sample size. And we find that as n increases, t-distribution approaches a standard normal distribution. So that means when n is getting bigger and bigger, we will find that the t-distribution curve will be the same with the z-distribution curve. And next one, in mathematics, we will find that there is not only one curve for the t-distribution. That means t-distribution is not a unique distribution, but instead a family of distributions indexed by df. So what's the meaning of df? That is degree of freedom. Degree of freedom. So most often we use this character, this Greek character, to represent the degree of freedom. So that is df. So this character sound new and is equal to n minus 1. So that is the degree of freedom. And we will find that if the new is different, the shape of the t-distribution curve is different too. Actually, this number is associated with the number of the sample size. So actually, the shape of t-distribution curve is influenced by the sample size. We just use another number, we just use another one to represent the influence of the sample size. That is nu, the degree of freedom. And the pth percentile of a t-distribution with n-1 is denoted by this one. And we will find that in the right corner of the little t, we use n-1. That is the nu, right? That is the degree of freedom. And we said that if the nu is fixed, that is a fixed number, the shape of the t-distribution is fixed too. So if we don't know the nu, what is the exact number of nu, there will be so many curves for the t-distribution. And each curve has a different shape. So we cannot tell the exact t value. So we will find that when we are talking about the t value, we need to know the nu. And this one, p. P is similar with what happens in Z distribution. In Z distribution, we said that the P is actually alpha. That is the area under the curve, right? So here, they have the same meaning. So this P means the area under the curve. So we find that we need to know two numbers of the t-distribution, and then we can find the exact t value. This is used for one side. That means the P, the area and the curve is in the only one side, left or the right side. But when we are talking about the two sides area and the curve, we need to use this one. We find that n-1, that is still the degree of freedom, and we find that this is not p, that is half p. That means we have two parts of their area and the curve. The first part is in the left side and the second part is in the right side, and the left plus the right equals to p value. So that means in one side should be half p, and in the other side should be half p too. So we use this one to represent the t value of the two sides. But there are something very special you need to notice that. We can find the exact t value and its corresponding probability. But the t values are not listed in the table A1 because we know that the table A1 is the value of the Z distribution. So all the numbers for the t value are listed in another table, that is in the second table. That is table A2. So table A2 is specifically constructed to assist in hypothesis testing by listing only the percentiles most commonly used. So in table A2, not all of the t values are listed in the table. It's just a small part of the whole t-table, and the probability in the t-table is what we most commonly used. So that is different from the table A1. In table A1, we can find any number of z value with its corresponding probability, but that is not the same in table A2. And the second one, since the distribution is symmetric about 0, so the percentiles below 0.5 can be found by affixing a minus sign to the corresponding percentile above 0.5. That is the same with what happened in z distribution. And we said that the distribution is symmetric about 0. So in our book, in table A2, you will find that all the t-values are positive numbers. So if we need a negative number, you cannot find the negative number in table A2. But we know that the t-distribution is symmetric about 0, so we will know that the negative number and the absolute value of this number has the same probability. They has the same area under the curve. And the last thing you need to notice, that is, in this class we won't discuss the problem of one side. So that means all the questions, all the hypothesis test should be based on two-sided test. Okay, so next one, let's look at this picture. So what is the shape of the t-distribution? So what is the t-distribution curve? In this picture, that is t-distribution. We will find that it's nearly the same with the z-distribution, because we find that the curve is symmetric about 0, and the curve has a single peak. And we will find that the tail of the curve, they have two tails, right? The left and the right. And we found that the two tails of the curve is getting closer and closer to the x-axis. So that is the similar with what happened in z distribution. But we will find that they have some different points. For example, in this picture we can find 1, 2, 3 distribution curves, and they have different shape. Someone of the 3 is taller, but someone is not very tall. Someone is wide, but the others are not wide. So the difference between the shape of the t-distribution curves is based on a special number, that is the df, namely nu, the degree of freedom. So we will find that when the nu is changed, the shape of the t-distribution curve is changed too. And in mathematics, we will find that when the number of nu is getting bigger, and bigger, we will find that the curve is getting taller and narrower. So in this picture, we will find that there are three t distribution curves, and this one has the biggest nu, and this one has the smallest nu. And according to the properties of the t distribution, we will find that when nu is getting bigger and bigger, t distribution is get closer and closer to z distribution. And we will find that the curve is symmetric about t equals to 0. Okay. So here, let's think about it. When t equals to a negative number, for example, 3.2, negative 3.2. And when we are talking about the area and the curve, actually we mean the area of the tail. So this part, that means the part when t is less than negative 3.2. And the area of this part is actually the probability. So the t value, we can denote it as for example, this is the curve of degree of freedom equals to 5. So we can use this one, 5, p equals to minus 3.2. So this is the probability, or this is the area and the curve. Okay, so now let's think about this is the p, and how about the probability when t is bigger than or equal to positive 3.2? Yes, we will find that they are the same, right? The probability of these two, they are the same, because we have mentioned that the curve is symmetric about 0. Yes. So both of these two sides has the same area. Okay, so that is t value and t distribution. Okay, so now let's think about that. How can we get the t value and its corresponding probability? I have mentioned that we can use a special table, that is table A2. So how can we use table A2? Let's turn our page to the appendix table A2 in page 152. Okay, it's here, table A2. And let's look at the title of table A2. That is the critical values for the t distribution. So please notice that this table is used for t distribution, not z distribution. And let's go back to the table A1. We will find that the table A1, the title of table A1 is for standard normal distribution, that is z distribution. So we often call it Z table and table A2 as T table. Yes, so let's look at it. The table is different with the table A1. So we will find that this part in the first column, that is not Z value, but df. df is the new, namely degree of freedom. New equals to n minus 1. So in this table, all the df numbers are listed in the first column. So when we want to find a special number of t value in table A2, the first thing is to calculate the number of new and then find it in the first column. And next one, this part in the blue color, we will find that this is the p. That means the p, the probability, and actually that is the corresponding area and the curve. And we can find that there are two rows. The first one is one-sided and the second one is two-sided. One-sided means only one part or only one tail in the left or in the right, but only one. And two-sided means left plus the right. And we know that left and the right, they are the same. So actually, two-sided equals to one-sided times 2. So we find that when the number of one-sided is 0.25, its corresponding number of two-sided is 0.5. That is the number of one side multiple 2, right? Okay, so here we will find that in this table, not all the numbers of the probability are listed in the table. There are only some special number which are commonly used are listed here. For example, 0.5, 0.2, 0.1, and the other numbers. And we said that in our class, we won't talk about one-sided test. So the only thing we should know is the number in the second row, two-sided. But please notice that you don't need to remember the numbers. You don't need to remember any numbers in table A2. That's very difficult. I cannot remember all the numbers in table A2. So you don't need to remember any number in table A2. When we use the t-test, when we need table A2, we can find the special number in the book. So you don't need to remember any number of the table A2. Okay, so now let's try to find some special t values with the help of table A2. So how can we do that? Let's do some exercise. The first one, let's try this number. And here we have mentioned that this is the t value. And we explained what's the meaning of these two numbers located in the right corner of the t table. This one, this number 10, that is the df, right? New equals to 10. And we find that the p, the probability is 0.05. 5. And we find that this one is one-sided, right? Because we said that when we are talking about the two-sided t-value, we need to use half p. So there is no half, there's only one number here, right? 0.05. So that should be one-sided. Okay, so let's find it in table A2. Let's remember these two numbers. The first one is df equals to 10, and the second one is p, one-sided p equals to 0.05. Okay, let's find it. Let's go back to the table A2. The first one, you need to find the df in the first column. Oh, it's here, 10, right? So that means the t value are listed in this row. And the next one, let's find the p. That is one-sided, and the p equals to 0.05 is here. So that means the t-value should be listed in this column, and we can find that the number located in the cross is 1.812. So what's the meaning of that? That is, let's write it here. T equals to 1.812. So what's the meaning of that? Let's draw the t distribution curve here. It's symmetric about 0, and this number is a positive number. It's here, 1.812. So that means the area and the curve is 0.05. But the further thing you should notice that is the degree of freedom is nu equals to 10, because we said that when the number of nu is fixed, the shape of the curve is fixed too. So we need the shape of the t distribution. So the first thing is we need to know the fixed number. And when nu equals to 10, we will find that when t is bigger than or equal to 1.812, this area, this right tail, this part has the area of 0.05. And the area is also the probability. So that means when t is more than or equal to 1.812, its corresponding probability is 0.05. But we find that this part, only the right side, without the left side. So we call it one-sided. And how about two-sided? Let's try another number. This time, let's try this one. 12 half 0.01. So let's go back to the textbook. The first one, when nu equals to 25, right? And this time we notice that that is two-sided, right? Because this part, half, right? So that means two-sided and 0.01. So this number. Okay, so here in the cross position, this one, 2.782. Let's write it here. Equals to 2.787. So what's the meaning of this number? In a t distribution, when nu equals to 25, the curve has a different shape with the first t because the nu is different. And we found that because the t-value is based on two-sided, so it has two parts on the curve, the left tail and the right tail. And the number of t is 2.782, but you should notice that this is the positive t-value. When we are talking about the two-sided, that means there are another number of t in the left side. So we know that the curve is symmetric about 0, so in the left side, the number of t should be negative 2.787. Although there are not negative numbers of t-value in table A2, but you should know that because the curve is symmetric about 0. So the meaning of the number is if t is more than or equal to positive 2.787 or t is less than or equal to minus 2.787, the probability should be 0.01. Actually, this part, when t is more than 2.787, we will find that this part is here in the right part, right? And another one, p is less than or equal to minus 2.787. That is in the left part, the left tail, right? And this part in the left plus the part in the right, that is 0.01. So the left part, the probability of left part is half of 0.01, and the right corner, the right part is 0.01 over 2. They are the same. And these two parts, if we sum it up, we will find that the whole probability should be 0.01. So when we are talking about the two-sided t distribution, that means outside the two numbers of t, negative and positive. For example, outside the negative 2.787 and positive 2.787, the probability should be 0.01. Okay, let's take a few minutes break.